1, 2, 3, 4, 5, 6, 7, 8, 9, only about 10 people, looks like 11. Yep. So we're going to get going anyway. I've got another class, and I guess a lot of you do too. I do want to point out one other administrative thing besides the midterm being slid 1 week to the 14th. I'm going to try to use a classroom polling system next week. On Wednesday is when you need it by. I'm going to be trying to get something called iClicker moving. One of the iClicker company, like a lot of the education publishing companies and education support companies, they're letting their products out for free for the rest of this semester. And we've got evidently a site license for free to use it at Washington College. And I'll be getting that to you either in an email or I'll talk about it on Class Monday. Because what I'll do then is I'll flash up a slide, and it'll ask you a question. Choices will be A through usually D or E, 4 or 5 parts, and it'll be directions using right-hand rule mostly initially. And then you go in with iClicker and put your response. It's a little bit more anonymous than me expecting you to chirp in on the recorded video that we're making in Zoom. So that's my hope. If you've already got it for another class, I think you should be set. I just have to figure out how to set it up for my class. I assume there's some sort of user ID that I give you, and then you can log into it. So that's what we'll be doing hopefully next week, Wednesday. As we said, the lab will be next week, Circuits 2. I'll be getting that. I'll be videotaping that today and over the weekend. It should be posted up just like video 1 was. And it looks like I've got 17 people have submitted. Whoever the last 2 are, please get them in. I'm going to be grading it today, and that's that. And then, of course, the midterm the week after. Any other questions on administration? All right, then I'm going to go right into the material for today. We're continuing on talking about magnetic fields. And if you remember, when we talked about electric fields, the first thing we did is we figured out, well, how do we create these electric fields? And that's what we're doing right now. We're going to spend 4 days talking about ways to create magnetic fields, how you can calculate what the magnetic field is around a moving charge or a moving charge in a wire, which we call a current. And so that's what we're going to be doing. All right, so let's share the screen here, which should be that guy. And I want to review the right-hand rule initially. Come on, pop up. Okay, there it is. And it's got the green border around it. And we'll go back to the right-hand rule, and we'll put our pictures away so they don't interfere with the video. And, you have to be able to do cross product, because integral to understanding magnetism, calculating magnetic fields. And then next week, when we talk about forces on moving charges or wires in magnetic fields, right-hand rule is an important part. And, one of the things I would tell you is I'm telling you my way of figuring out the direction after you've multiplied 2 vectors using a cross product. I recognize that in math classes, in high school perhaps, or maybe somewhere at another institution or Washington College, you may have seen a different method. And that's okay if you can get the problems right. I've been teaching for quite a while now. I was trying to do a count of how many physics textbooks I've taught out of in my teaching career. And I think it's either 6 or 7. And Knight actually is the one book, our textbook is one book that shows a different method for determining the direction of the resulting vector after multiplying 2 vectors via the cross product. But I'm calling vector C in the slide that hopefully you're looking at here. 5 out of the other 6, you point your index finger, number 1, right, in the direction of the first vector. I think that's why people use this technique more frequently than what our textbook does. Index finger, number 1, first vector. Middle finger, the one I hurt and have splinted up here, that's the second finger. That gets the second vector. And then your thumb points in the direction of the resulting vector. And people have figured out, well, I can either point with my middle finger, or I can push towards my middle finger away from my index finger. That accomplishes the same thing. I have an angle between 2 vectors, and my thumb points to the resulting vector. Now, there are other methods, though, because all you have to be is cyclic. Remember, I cross J is K. And so you just need a pattern where you've got 3 cyclic things. Most people go index finger, first vector, middle finger, and then your other fingers to second vector, thumb points in the direction of the resulting vector C. But there are other ways, and our textbook has another one. If you learned another way in high school, that's fine. We'll just do that. Now, but here's the point, I guess. At the end of the day, if I draw two vectors, like let's say I've got, there's vector A, okay, and there's vector B, where is C, the cross product of A and B? And you know, in a problem like this, there's 6 choices: up, down, right, left, into the page, out of the page, right? Well, I could just give you a clue. A is into the page, right? That's what this means. You're seeing the fletching of the arrow going away from you. B is up. The cross product is in neither of those 2 directions, right? That's the first point to emphasize. This plane here that contains vectors A and B, the answer C is perpendicular to that plane. And so that leaves 2 directions. It's either to the right or it's to the left, right? That's the question. Correct, I should say, not right. Is that right? Right. Okay, so the thing to have to decide here is which way is vector C, and whatever method you use, you have to be able to figure this out. And I would say point your fingers, first index finger in the direction of the first vector into the page. Okay, my middle finger goes in the direction of the second vector, which is B, 2 to B, the second vector. And then my thumb is pointing to the right now as I'm doing this, and that's the direction of vector C. And so that tells us that that's the right answer. And hopefully you were doing that along with me via whatever method you have. If you don't have a method, I would recommend mine. It is the most widely used method, but there are others. And if a teacher in high school taught you something and you're successful with it, don't change. Okay, I'm telling you what to do if you don't have it right. We'll do a couple more cases here. Let's have vector A be this way, vector B be into the page. And again, I want to know what is vector A cross vector B. And if we were doing this iClicker right now, I'd be just stopping and I'd say, okay, everybody put that answer into iClicker and I'll see what people think. But just take a second right now and in your own mind, the way you do it, okay, figure out what is the direction of the cross product of A and B, just like I've got right here. And I'll just take a second and think about it. And you know what I always recommend to people is there's nothing that says you can't, like, it's hard to turn your computer screen, but turn your paper. You know, just like GPS, that guides you on your cell phone or on the dashboard of your car, it always has a direction you're going up. I would turn my paper so that the first vector is in the direction it's easy to point, right? Otherwise, you got to do all kinds of contortions with your arm. But so there's nothing that says you can't turn the paper, so A is this way, right? Then B is into the page, and so I am going to turn, and if you can see me through my camera, A is the first vector, B is into the page, the second vector, and my thumb is pointing straight up into the air. And so that tells me that the direction has to be that. And again, the other possibility here would have been down, right? But vector C is up. A cross B is C. And that's I guess, very similar to this one. If you think about it, I've just rotated it a little bit. Whatever you do, you got to be able to get these directions right. As a general rule, if you're asked in a physics class, and I would say any other follow-on science class where vectors are discussed, if you're asked for what the answer is to a vector, you're obligated, and you should know, first of all, that the thing you're asked about is a vector, and then the second thing is you're obligated to give both the magnitude and direction, or perhaps components. This is true in math as well, right? Unless the problem specifically says, hey, what's the magnitude of the magnetic field? Then you're not responsible for the direction. But if the problem just says, what is the magnetic field? It does expect you to find the vectors. And you should have hopefully looked at the problem, I think, on worksheet that is due today, the Biot-Savart law, and you had, I think, 2 wires. And if I remember right, the current was going into the page in both cases. And you were asked to find what the magnetic field is up at this point here. And you should realize that was a vector addition problem, right? The first problem is to find the direction of the magnetic field from each of the wires. And so if this is wire 1, I'm hoping you'll see, because of another right-hand rule we discussed way back, up there it is, this right-hand rule, that if you swirl, or you put your thumb in the direction of current, your fingers swirl in the direction of the magnetic field. Okay, let's come back to the worksheet problem I'm hopefully helping you with. And I suspect I'll see people at, keep going, other one. There it is. Okay. I expect I'll see people at office hours, which will be at 2 o'clock again today. I'm sorry, 1 o'clock to 2 o'clock today. Again, if you got questions. And if that time doesn't work because you're in another class, please, by all means, shoot me an email saying, hey, I really wanted to come to office hours, but 1 o'clock just did not fit into my schedule. I'm doing another synchronous class. Let me know. I'll come up with a time that for everybody. I don't want to exclude anybody by my arbitrary choice of times. As I think I told you, I'm not going anywhere. All right, anyway, there's the magnetic field due to 1, because if I put my thumb into the direction of the current, my fingers swirl around, and most people got this right on the worksheet I graded last night. So I may have just changed the orientation here. There's the magnetic field from 1. 2 is a little bit harder because you notice there's what that vector I would have called R, right? And so the magnetic field is always perpendicular to that thing. Okay, there's magnetic field 1. There's R for the second wire, and the magnetic field from the second wire is right there. Now, I think I haven't drawn these of a reasonable length because I think B1 is closer, so it's probably a little longer. So maybe I shouldn't have it that way. So if I'm going to scale, maybe that's what I should write. Okay, that B1 is probably, if the currents are the same, and my recollection is they were in this problem, then B1 is a little bit longer, and that's what you should be doing. So the problem on the worksheet that's due today is one of vector addition, right? You have to add B1, which of course is horizontal, only has an X component. You've got to get 2 components of B2 and add them together. And as I said, if you're asked for what is a magnetic field, which is a vector, you either have to calculate magnitude and direction. In this case, I think the best way is just give me 2 components. Give me an X component and a Y component, unless it specifically says what is the magnitude and direction. And I just don't remember what the question asks. Right? Any questions on that worksheet problem? Okay, and of course, you're using the result that we came up with for a long straight wire. You're using that result for both the 2 wires to calculate the magnetic field, and then you're adding them up. You're adding them up like vectors add up, because the 2 vectors are not in the same direction. Okay, and so that's the picture. And you know, I often see people who try to answer that question without drawing a picture, and I think that that's not a good technique. Let's just hold it at that. I remember the movie Good Will Hunting, where Matt Damon plays this exceptional mathematician who just sees mathematics in his head. And I think I may have told you at the start of the semester, that's savant-like behavior. The rest of us draw pictures and work things out. And that's just an example of such an occurrence. I can't add those 2 vectors in my head without drawing them. And I've been doing this for a whole lot longer than you all have. But a lot of you are smarter than me, so that could compensate, but I still recommend drawing the picture. Okay, so that was the magnetic field equation we had for a long straight wire. We know how to get the magnitude. We've got the right-hand rules to get us to a direction. Okay, there's that right-hand rule again for these wires. We were talking about a loop of wire, and we said this isn't a general result down here, but this is where we ended off on Wednesday. We developed an equation like this, and I do want to point out the equation for a long straight wire and this equation that we developed. My internet connection just popped up as being unstable, so I assume my voice may have been lost right there. This equation for the loop of wire and the previous one for a long straight wire, not something I'd ever expect you to derive. That calculus is above and beyond something I would ever ask on a test. However, if you should be able to look this equation up, you should know that it exists, and this equation allows me to find the magnetic field anywhere along this x-axis right here. You plug in the value of x, you plug in the radius of the loop, and remember this is a loop, looking at it from the end, it's just a circle of radius r. Okay, so you put those numbers in, you plug in the value of the current, and you can get the magnetic field. And I think the last thing I said before we quit on Wednesday was if there were multiple loops in a device we often call an electromagnet or sometimes a solenoid, this would be the magnetic field from each one. So just multiply by however many loops there are, and that would get you the total magnetic field again. And our assumption is that all the loops are on a spool sitting right on top of that single loop that I've drawn right here. Okay, but you can see it's a useful equation. I don't remember if I talked on Wednesday about how to get the direction of this. I hope I did, but here's the rule. There is now a third right-hand rule I'm going to tell you. in this case, current might be going around this circle like this. And that's kind of what I'm envisioning if I put my eye right here and look down the axis, okay, at this thing. As I look at it, you can see the current is coming out of the page at the top. So that would be going to the left up there in this view. And then it's going into the page at the bottom. So that would be that way at the bottom. And I guess the right-hand rule is if you swirl your fingers in the direction of the current, your thumb will point in the direction of the magnetic field, which is that thing right there. All right. And so that's kind of a third right-hand rule, thumb rule. We've got three now. How to just do cross product, index, middle, thumb. And then we've got the wire, the long straight wire. You put your thumb in the direction of current, your fingers swirl around in the direction of the magnetic field. And now this time you're going to swirl your fingers around in the direction of the current, and your thumb is going to point in the direction of the magnetic field, depending on what the orientation of the plane of the loops are. Okay, and that's an important idea. Three right-hand rules to get you direction. But we did kind of show that here using the DS cross R hat direction. That's a little tedious to try to get. Let's see, current's coming this way, R's that way, magnetic field's out in this kind of odd direction that I drew. We got two components. We recognized that component canceled as you considered pieces of the wire all the way around, and so the magnetic field was always in that direction, in the positive X direction. It just seems to me a whole lot easier to have a rule where I go, let's swirl my fingers in the direction of current. That's the direction of the magnetic field. Okay, and so moving on from that today, I do want to make a point. What is the magnetic field right at the center of this loop? Well, hopefully you realize at the center of the loop, that right there, that point was X equal to 0. Okay, X equal to 0. And that simplifies things because that guy goes away. And then you have R squared to the 3/2 power. The 2 and the 1/2 cancel. And so I guess that's R cubed down in the denominator. So I can get rid of that, and that just makes it an R cubed. But if you recall, there was an R squared up in the numerator. Okay, so that R squared right there and that R cubed just cancels, and there's just an R in the denominator. So permeability of free space, 4 pi times 10 to the minus 7th Newton per amp squared, times the current divided by twice the radius of the loop. That tells me how big the magnetic field is right there at the point X equal to 0. And then hopefully you can see, I'll even try to sketch that a little bit. I think that would be the maximum value, right? That's the value of the magnetic field. And then as I move outwards along the x-axis, I expect the magnetic field to decrease as I get further and further away. So that might be a plot of what the magnetic field looks like as a function of how far away I am from the center of the loop. And this is a handy equation to have. You know, if somebody ever asks you what's the magnetic field right at the center of a loop, there it is. You don't have to, you just have to know the dimension of the loop. What's the radius of the loop? Be careful, like most things, intermediate physics classes or sometimes alertness drills, maybe we'll give you the diameter of the loop. We do that all the time. It's what's easiest to measure is the diameter. Remember to divide it by 2. That is an R for radius. Okay, so now that brings us to an interesting comparison I want to make between this loop of wire, where this was the magnetic field, simplifying it at the center, and what I started talking about on, I guess, Monday, a bar magnet. And I referred to this on Monday, this bar magnet from ferromagnetic materials, iron, nickel, cobalt. I refer to that as a dipole, because it looks a whole lot like the electric dipole we talked about, you know, where we had a positive charge and a negative charge, right? Negative and a positive charge. And we were finding electric fields around this, right? And so we had these electric dipoles. Well, this thing looked a lot like an electric dipole, and so we refer to it as a magnetic dipole right here. And so does a loop of wire. I guess that's the point. If you compare these two things, you'll see that the magnetic field lines on a loop of wire look very similar to the magnetic field lines from a piece of ferromagnetic material, permanent magnet. Okay, so this loop must also be a dipole. And just like we defined for electricity, a dipole moment vector, and remember this was Q and this was Q, and the separation between these two things was some distance L. I guess I'm getting better at writing with my mouse. We said that the electric dipole was that charge times that length L. It always has a dimension and something about the charge, okay? And it's in the direction from the negative charge to the positive charge. So the dipole in this case was P in that. Now that's not well drawn. I'm gonna erase that and try again. Come on, there's the eraser. Erase that and try again. Pen, 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 there we go. So the dipole moment vector for electric charges was in that direction. We're similarly going to have a magnetic dipole moment vector. We're going to call it mu. I'd argue, and you might as well, that's an unfortunate choice since our constant is the permeability of free space, also a mu, but subscripted with a 0 and a scalar, of course, so that's one of the differences. Why we couldn't come up with a different letter for the magnetic dipole moment vector is a darn good question, and I have no answer for it, and I'm not defending it because I didn't do it. But in the same way that a charge times a length is an electric dipole, a magnetic dipole is a current, we're talking about the current in this loop here, times the area of the loop. And again, the direction of the dipole moment vector is normal to the area, and the normal we're referring to is the one that is caused by swirling your fingers in the direction of the current. Thumb points both to the direction of the magnetic field caused by that loop and also the magnetic dipole moment vector, which is consistent anyway. So both in this case over here, B is in this direction, the magnetic field that you calculate, but the dipole moment vector of that dipole, not P, it's mu, right, is also in that. So I'm going to cross that out. Won't make you, that mu is also in that same direction. Okay, current swirls around, coming over the top and towards you, it looks like in this picture to me. And so that gives both of those two vectors, puts both those two vectors in a particular direction. This will be more important next week when we talk about forces on wires in magnetic fields. If we have a loop in a magnetic field, it's going to tend to rotate, much like an electric dipole rotated in an electric field, right? And so we're going to see that next week, and we just want to make sure that's out there and clear for you. What is the definition of a magnetic dipole moment? This is it, 3 bars. It's really a definition. You just have to accept it. You may ask yourself then, what is the current we're talking about in a permanent magnet that gives it its dipole nature? And I would say it's the swirling of the charge, the electrons swirling around the nucleus, not orbiting. I like the word swirling because I don't want to evoke planetary orbits, and kind of the charge on the electron swirling around the electron. We call that the spin of the electron. Those two things contribute to permanent magnetism because, again, it is a little loop of current going around in a circle. Okay, and that's what we think a permanent magnet dipole is. In any event, if I take this equation right here that we worked up yesterday for the magnetic field from a single loop of wire, and you notice what I did here is I just multiplied by pi over pi. It's a handy thing to do. I can multiply by pi over pi because that just means I multiplied by 1. It's an identity matrix kind of thing, or identity kind of multiplication, doesn't change anything. The reason I did that is because then right here I have pi times the radius of the loop squared. And of course, that's the area. And the current times the area was already there. So that is the magnetic dipole moment vector's magnitude sitting right there. And so you can, if you remember this equation, you can calculate the magnetic field from the permeability of free space times the magnetic dipole moment vector's magnitude divided by 2, that pi I inserted, and then that same factor, r squared plus x squared raised to the 3 halves power. This again demonstrates the unfortunate choice of notation for the magnetic dipole moment vector being mu, because right there you look at that and you go, okay, that one's 4 pi times 10 to the minus 7th Newton per amp squared. This guy is the dipole moment vector, which has units of amps times meter squared, right? Current times meter squared. And of course, down in the denominator here, you got meters squared to the 3 halves power. So that's meters cubed. And that must turn out to be a Tesla, a Newton per amp meter. And it does. But that's, you can see, that's our deal, I guess. And that's how we calculate it. Now, we want to make the comparison to the electric field around an electric dipole. And I think the point is, if you're very far from this loop, so that x here is much bigger than r squared, and so that would be like across the room from this dipole, where that distance x is very big, I can ignore then what R is, and you should see that the magnetic field around a dipole decreases as 1 over the distance to the third power. And that's a pattern that we saw for electric fields too, right? Electric dipoles also had electric fields that decreased as 1 over the distance cubed. We did a simulation with a FET in lab that showed that. Point charges, which you can't have for magnetism, right? There's no such thing as a point charge like object. That would be a monopole. We think those don't exist. If it did, it would hopefully decrease as 1 over r squared to be consistent with a plus or minus charge for an electric field. You notice that lines, like a charged line, the electric field decreased as 1 over the distance to the first power. And that's exactly what we found for magnetic fields around a line of moving charge, line of current. The magnetic field decreased as 1 over the distance to the first power. We don't talk much about sheets of charge, moving charge here, but you might guess that that magnetic field near the sheet would be constant, and you would be correct. Okay, and so that's just what I want to say. I think this slide summarizes a little bit about what I just said. There's the electric dipole, which we call P, okay, and it's oriented in this case upwards. Nope, I'm sorry, it's oriented downwards. It's always from the negative to the positive charge. And the electric field around a dipole decreases as the distance to the third power, and that's what we just showed for the magnetic dipole. And of course, in this case, the magnetic dipole moment vector would be oriented that way. Okay, and moving on here a little bit. Got to change gears. I'm not going to get too far into Ampere's law. We'll pick it up again on Monday. But Ampere was a pretty smart physicist, again, funded by Napoleon, right? French name, Biot, Savart, Ampere. You can think of a number of mathematicians, right? Legendre, Laplace, Fourier, all these are mathematicians who lived in the 1800s and were funded by Napoleon to do research. And it's no coincidence. In any event, I want to recall what the definition of an electric potential was, okay? And it was this E dot dl integral. And really this just meant E times some dx maybe, if it was an x component of the electric field. If not, you'd have to introduce a factor of cosine of theta, because the dot product, unlike the cross product we've been using now, it deals with the cosine of theta. The cross product deals with the sine of theta. And so that was our definition. And one of the things that we were clear on, in fact, it was the basis for what we were doing in circuits last week, Kirchhoff's loop equation, is if you move around a loop or around any path from the starting point A and you come and you replace B here back to where you started from, well, the potential between any 2 points, the electric potential difference between any 2 points, hopefully you can, as I'm talking about this, you're thinking, well, I know the answer to that. The answer is 0. And the notation we use, the mathematicians like when we go around a closed loop like that, is on the integral sign, they throw a little circle right there to say, hey, I've gone all the way around some closed path. That just means the limits of integration are themselves, are the same, okay? And of course, this could be just E times dx if you want, if the electric field is in this direction. And if the electric field is constant, as it was very often, it was just electric field times some distance. But if that distance means you come right back to yourself, the distance goes to 0. And again, this is 0. So that's what's true for an electric field. And the words we use when we see something like that is we say, well, the reason for that, here's the word, the electric field is conservative, right? And that means if you integrate it around a closed path, 0 work is done. IVE, okay, conservative. All right, so here's the question, I guess. Let's try the same thing for a magnetic field, right? I've got this long line of current right here. Let's integrate around the closed path, maybe start at capital A, go all the way around. I guess that's be counterclockwise as viewed from above. It's the thing about clockwise and counterclockwise, they're kind of ambiguous, right? The wall, as you look at it with the clock on it, the clock is going clockwise around. But if you're in the room on the other side of that wall and you think about what direction the clock is moving, the clock hands are moving counterclockwise. So whenever you say words like clockwise and counterclockwise, you have to remember that's ambiguous. You have to specify a perspective. So I'm moving around this loop clockwise as seen from above the plane, okay? Whereas below would be counterclockwise. Anyway, what would be the integral of not E dot dl like we did for electric potential, but B dot dl. What would it be? Well, as you recall, and you don't have to necessarily memorize it, you just have to be able to have the wherewithal to look it up. That was our equation for the magnetic field. And it was, think about the right-hand rule, if you put your thumb in that direction of current and you swirl your fingers around, that would be the direction of the magnetic field. So this dot product is unnecessary in this example, right? Because the magnetic field is going around that loop, and the direction of that little incremental path around it is also going all around the loop. They're in the same direction. And so you just multiply them together. As often happens in problems dealing with Ampere's law, the integral of this dl around a closed path is just the length of the closed path, which in this case is circular, circumference of a circle, right? I heard a joke from Ms. Mary Lynn Kersey. She said there was this weight problem from this guy named Circumference, and I never mind. It was a silly joke she had. He had a problem with his weight. Never mind. His circumference was too big. Never. Any event, circumference here, 2 times pi times r. You sort of have to be able to look that equation up. There's my magnetic field. That is the meaning of B dot dl. And if you notice, 2 pi r here, 2 pi r here cancels. Well, first observation is that's not zero, okay? Like it was for electric fields. It is just a constant times how big the current is, and that current, you'll notice, is passing through the area bounded by that loop right there that I integrated around. Okay, and it was an arbitrary loop. I chose it. I picked that loop. It wasn't there physically for any reason. The only thing that physically was there was that current carrying wire. I constructed this loop kind of in the same way we constructed surfaces to integrate electric fields on when we were doing Gauss's law. And so this should evoke some of that same kind of methodology. But what's the conclusion about magnetic fields? If I don't get zero right here, I got an answer, mu zero times I, a number, a non-zero value. Apparently magnetic fields, they're not conservative, are they? Because if they were, when I integrated a magnetic field around a closed path, again, that's what that symbol means in the integral, I would have gotten zero. I didn't. I got mu zero times the current. And that's what Ampere worked on. And he realized that that result is not a fluke. It is a general result. And it could be used to solve problems for magnetic fields in the exact same way that Gauss's law, and I'll write that up here, the integral of E dot dA though, right? Not dl, we had to pick a closed area here, was equal to the charge inside divided by a different constant, the permittivity of free space. My internet connection just was looking bad there. Well, now I've got B dot, but now I'm integrating not over a closed area like we did in Gauss's law, but a path that I have to define. And in the same way, in order to use Gauss's law, I had to pick a surface. It was often a sphere, right? Or sometimes it was a cylinder. Here I have to pick a path. I have to pick a closed path. And, you know, probably 90% of the problems we'll do, that path will be a circle. There'll be a couple problems where that path might be a rectangle. But we're going to pick those things such that the magnetic field on those things is hopefully a constant. I could bring it outside. And then the integral of dl on a closed path is just the perimeter of that path. And when it's a circle, we call it the circumference, 2 times pi times r. If it's a rectangular thing, it'll be the sides all added together. Perimeter is what that's going to be. And, you know, I don't mean to trivialize the calculus here, but just like Gauss's law always became an electric field times a surface area on a closed surface, this integral of B dot dl will always be a magnitude of a magnetic field times some perimeter, okay? And more often than not, that perimeter is going to be the circumference of a circle, 2 pi r, okay? So the integral, you have to pick that thing though, and hopefully you pick the radius of that path, if it's a circle, to be exactly where you want to find the magnetic field, just like you pick the surface in Gauss's law to have a dimension so that on the surface, that's where you were trying to find the electric field. The current then is any current that's passing through this shaded darker area right here, bounded by the path. and it's useful for solving symmetric problems. Only when there's enough symmetry can you apply Ampere's law. It's always true, but in order to solve for the magnetic field, you need sufficient symmetry. And I just want to recall what I said for Gauss's law back when we were talking about electricity. You had to try to imagine electrostatics, electric fields. You had to try to imagine a surface where the electric field was constant everywhere on the surface. You tried to get a surface so that you could ignore that that dot product, such that the direction of the normal to the area and the electric field were in the same direction. And then you had a good surface, figure out how much charge was inside the surface, write this as just E times the area, solve for the electric field, bring the area to the other side of the equation. On certain cases, we had to break that integral up into pieces. And what I'm thinking about is like a cylinder where we had to there's three areas to a surface. There's the two ends, and then there's the curved side. You might need to do that, and we might need to do that with our paths as well. But same idea here, where you try to imagine a closed surface. Here I got to think about a closed path, okay, just a line that's closed. More often than not, it's going to be a circle. I want the circle, the path, to have a radius so that that's exactly the same radius I want to find the magnetic field from, in most cases, the line, okay? And I'm hoping that the magnetic field and the path will always be in the same direction. Magnetic field lines do swirl around, so that should be pretty easy. And then figure out, instead of how much charge is inside a surface, how much current goes through the area, the surface area, which the path bounds. So a little bit difference here. When I say current inside the surface I'm referring to, if there's my path, it's that surface right there. It's the open surface that is bounded by the path I'm integrating around. All right, so talked enough. Let's give you an example and then call it a day. I want to look at a magnetic field around a wire, okay? And oddly, I want to figure out, well, what is the magnetic field inside the wire that is carrying some constant current I, okay? And so here's Ampere's law. And I picked a path. Let me just check one thing here. Yeah, okay. I'm doing the inside case right now. I'm going to do this path right here. Okay. See the symmetry of it? It's very reasonable to think, because of the symmetry, that where I just drew the X there and where I drew the X right there, the magnetic field's the same. I can rotate one of those points by symmetry into the other point. Anywhere on that path, I believe the magnetic field is probably the same. And because of that, it's a constant relative to this integral. I could bring it outside. And then I'm just left with integrating dl around a closed path. Okay, this dot product, that's pretty good too, because I still think that the magnetic field is just like that of a wire. It's swirling around as I'm viewing it counterclockwise here. Okay, I'm going to integrate around counterclockwise. And so I can ignore that dot product. Boom. The integral of B dot dl is just the magnitude of the magnetic field I'm trying to find times the circumference of that path. Remember before in Gauss's law, that would have been electric field times the surface area, circumference of a path. Okay, and there's a circumference of a circle here, which is the length of the path, the closed path that I'm integrating around. All right, the other side's a little bit harder to find. Current enclosed. Okay, what I'm talking about is the current which is going through there. Now remember, this current here in the wire, that's the total current going across the entire cross section of the wire, not the current going through this path. You can see that the current going through that path should be some fraction of the total current in the wire, right? Hopefully that makes sense. And so what I did here is I set up a little ratio, which I think is fair. The wire itself has a radius capital R, and I made, as soon as I did this, I made the radius of my path little r. It seems to me that the current enclosed by the wire is to the area of that path. Current enclosed by my path is to the area of that path, as the current going through the entire wire is to the total cross-sectional area of the wire. If you think about why that is, we're really saying that the current density is a constant, right? Current density is the total current divided by pi times the total radius squared. And if I'm looking at the current going through this area right here bounded by my path, that is the current that I'm talking about that is enclosed, or in, if you like, inside, whichever word you like there, divided by pi times my little radius squared. if the current density is a constant, these two have to be equal, and that's why this ratio was okay. Well, I think, let's cut my equation right there. The pi's cancel, right? And the current enclosed, I would just bring little r squared over to here. And so that's what I put in. The pi's cancel. I put in for the current enclosed, the total current in the wire times r squared divided by big R squared. And that's what I mean by current enclosed right there. And so just do a little simplification to solve for the magnetic field. And I guess the first thing I can do is cancel one of those guys. I got to bring the whole 2 pi in. I've already canceled both of those 2 pi's. So the 2 pi comes to the other side of the equation. Looks like I got the permeability of free space, 4 pi times 10 to the minus 7th Newton per amp squared, times the current, times the radius that I'm trying to find the magnetic field at, which is right there, that little r right there, okay, divided by 2 pi times the radius of the wire. Now, if you look here, that means the magnetic field is increasing linearly from the very center of the wire, where r would be 0 and the magnetic field would be 0. It increases linearly out to the edge of the wire right here. R equal to capital R is the edge of the wire. And so the next thing I guess we want to do is use Ampere's law to check what's going on outside the wire. And yeah, I did leave myself another slide for that. That's what I was checking before. Again, I'm going to use Ampere's law, and the results should be familiar. The results should be familiar. We've done it already, okay? So I'm going to, instead, since I don't want to find the magnetic field inside, I'm going to say, let's draw a bigger path, a bigger circle, and do exactly the same thing. I think the magnetic field is going around that way, so I don't have to worry about that dot product. DL would also be in that direction. It's tangent to that path everywhere, and so is the magnetic field. They're always in the same direction, okay? I think I have enough symmetry because that point right there, I would guess, has exactly the same magnetic field as out there. And so I could bring the magnetic field outside the integral. That's why I did this. Then I'm just left integrating around a closed path what the length is. And the length around a closed path that's circular is called the circumference. And that's just equal to mu 0 I. How much current is going through the area bounded by this path? Well, the words I would use would be all of it, right? All the current which is in the wire is going through that area. Of course, there's nothing out here in this white area, but all the current I is going through the area bounded by the path. And then that means the magnetic field, just bring the 2 pi r, the circumference over the other side of the equation. The magnetic field must be mu 0 times I over 2 pi r. We've essentially worked what I did a couple slides backwards, right? We've found the equation for the magnetic field for a long straight wire, which you notice decreases as one over the distance I am from the center of the wire. Okay, I mean, if you had a thin wire, the magnetic field would be something like that, and asymptotically approach at the very center of an infinitesimally thin wire. I guess magnetic field in principle goes to infinity, but that's not what's happening here. For a real wire, inside the wire, it cuts off and does that. Okay, so we've used Ampere's law to figure out what the magnetic field is both inside and outside the wire. The outside case we already knew, but I was a little surprised at the inside case. It wasn't clear to me that the magnetic field would increase linearly inside the wire, but it does. All right, we'll come back on Monday. Have a good weekend here. We'll let you out a few minutes early if there's no questions. We'll use Ampere's law to figure out what the magnetic field is in a solenoid, and then also something called a toroid, which is a solenoid that you wrap around into a loop like a donut, and that's referred to as a toroid. And we'll use Ampere's law come Monday in order to solve those two problems, and their results are fairly important. And then we'll be done talking about magnetic fields. All right, any questions on anything we've talked about? You all are very passive out there. Look and see if you can find iClicker on whatever smartphone you have so that you can download it. I hope don't pay anything for it. I hope to be able to get you a free pass account in order to download that thing. We'll do it next week. Remember, worksheet, and what worksheet number is that? Worksheet, I guess 25 is due today. I'll be at office hours at 2 o'clock to help anybody with that. Worksheet 26 will be due Monday. And I did add a homework assignment for chapter 29. 29 is a long chapter, so I've divided it into 2 pieces. There is a homework assignment for chapter 29 that you can get started on over the weekend that's due next Wednesday. Questions? Last chance? All right, look at that. I've gone over a couple times today. I'm about 5 minutes early. So you all have a great weekend. I hope everybody's healthy and doing well out there, and enjoy yourself. But why not do something to improve yourself? Study some physics, study your foreign language, study all your other classes, because what the heck, we're not going anywhere. Talk to you soon. Have a good weekend. Stop share and stop recording.